Welcome everybody to this new week of the course Big Data for Engineers. I will today finish presenting to you the white column stores, in particular how they are actually stored in HDFS. And then we'll move on to the next part of the course, which is about data modeling and in particular data frames that you might have heard. If you heard about the pandas library, for example, in Python, then this is pretty much what it is, but for a big data environment. Before we start, I have two questions to ask you to check your knowledge, and then we'll move on with the material. So, this is my first question. It's more of a taste, a matter of taste, right? But what is better? Good old XML, definitely. Simple JSON, definitely. They are totally equivalent as both represent trees and documents can be very easily converted from one to another, or it depends on the use case at hand. Okay, let's close it. So that's very nice. You actually gave my favorite answer. So I warned you that it's a bit sometimes a matter of taste and you can easily land into very big debates. However, if you got what I said, that it depends on the use case, then this is perfect because it means you have an open mind and you probably understood now that XML is perfect for publishing things like papers and any text that is tagged. So that's why publication companies really like XML. And if you really just want to store data like data frames, as we will see soon, then the simplicity of JSON can be attractive, except that, of course, we have yet to build the entire stack for JSON that you already have with XML. All right, so this was the first question. And the second question is right here. I don't think I have asked it yet, so let me do it now. With which servers must the client communicate to create a directory and to get the blocks for a file? That's about HDFS, right? Is it with the data node for everything, or with the data node for creating the directory, with the name node to get the blocks, or with the name node to create the directory and the data node to get the blocks, or with the name node for everything only? And what do we say here? We have a majority for the name node for creating the directory, and indeed the data nodes to get the blocks. So indeed, this is the correct answer. You remember the the centralized architecture, right? Where we have the name node that is the central node that has the file namespace and all the information about what blocks make what file. But the actual blocks are stored on the data nodes, right? So there can be many data nodes, maybe 1,000 of them, 10,000 of them. As a consequence, we saw that for directory creation, everything happens on the name node. And if you want to get the blocks, the actual contents of the blocks for a file, then you get them from the data node. What you get from the name node is only the block IDs, not the blocks. Right? Okay. So now I'm going to come back to the slides and we'll get going. And here we go. So where were we? We looked into a brand new technology that brings back tables into the picture, but larger than a relational database management system as we know it from the 70s. And we saw that it runs on HDFS, but I haven't fully explained to you how that is actually implemented on HDFS. This is what I'll do today. Remember the data model? We have pretty much a table, right? So in first normal form, there's a weirdly look at cells. In fact, some people do use the cells to actually put some complex stuff in there. So you can actually put an XML document here, a JSON document there. People actually do that, right? Then you would argue, okay, then it's not in first normal form, right? But HBase doesn't really care about that. HBase just lets you store whatever you want in the cells, and that can be any value, right? But for the purpose of the model, we are in first normal form. We saw that we have the row IDs that identify the actual row. They are sorted, right? This is very important. We have the column families here that group columns together that belong together, but we can have several of them. Column families are known in advance. They are a bit heavy if you want to add them later, but the column names themselves can be created just on the fly, just by making up new column names when you insert new tuples, right? Okay. Did I want to add something? Okay, slipped off my mind, but let me continue. So we saw that we partition things because we love to partition things in big data. We partition files into blocks in HDFS. And here we like to partition the rows as regions, right? With a minimum inclusive and maximum exclusive. And furthermore, we also partition in column families, and this is what we store together in HDFS, right? So this is the intersection of a region and of a column family. This is what we'll call a store for the purpose of the lecture, right? We saw that we also have decentralized architecture where instead of name node, this is called HMaster, and instead of data node, it's called region server. We saw that these are actually the same machines as name nodes and data nodes. They just co-run on the same machines, right? The HMaster together with the name node and the region server together with the data. All right. And remember what I told you, a region server does not store the data. It is responsible for a region. This is very different. The actual storage is in HDFS, as we will see. Okay, so this is my cake. You know, I probably also like chocolate cake just as much as I do. So we sliced our cake like this in horizontal and vertical slices. And every one of them is a store. And now we are going to look at one of the stores and see how this store right here or this store right there is actually stored in HDFS. So remember that a store is made of a region. That is the responsibility for that region is on some region server. And we have a column family right there. And then what we had is the column names and the row IDs. And then the intersection of a row ID and a column name is what we call a cell. It's a cell. And that has a value. It can be an integer, a string, even as I said, an XML document if you want to squeeze that into the cell, but it's whatever, basically, for our purpose. We don't really care what's in there. Okay, so now what happens is that this store right there is going to be stored in HDFS as one or more files that are called H files. H for Hadoop, HBase, H file, that's why it's called that way. So it might be one or more, right? It can be several of them. And I will explain to you why it can be more than one and how we actually get to create several H files. I will all explain that to you, right? But basically, one store is stored on HDFS as one or several H files like this. Now, what's inside an H file? Well, it's going to be boring and to the point that you might actually be disappointed by the demystification here. An H file is basically a sorted list of key value pairs. Okay, it's not the first time that we see key value pairs, right? We've seen them all the time. So once again, we have key value pairs. But how do I turn a store like this into key value pairs? Well, how do you identify a cell, right? What is the key for identifying a cell? Well, the key is the row ID right there, together with the column name, jointly identify here the purple cell. If I say A2, it's just like in this battleship game, right? So you have A2 that identifies the blue cell right there. So A2 is a key, B1 is a key, and so on, right? So I put here alphabetically sorted the keys A1, A2, B1, B2, C1, C2, and then I linked even all the cells. So red is A1, purple is B2, and so on, right? So you will figure out the spaghetti right there. But this is basically taking the cells, turning them into key value pairs where the key is the column and the row. And now I list my key value pairs in a sorted order of the key. And this is what I get. This is an H file. It's just key value storage, really. It's also called, for maybe some of you might know, at Google, it's called an SS table, this H file, the structure, the fact that you sort key values in a sorted order and you store them in a file that's called an SS table, right? Okay, but we'll call it an H file for the purpose of the course. It's a sorted list of key values. Okay, so far so good? Okay, so we store, a store as one or several H file, and an H file is a sorted list of key values, and each key value represents a cell in there. Okay, now there is more to the key, because it turns out that HBase supports versioning. What does that mean? It means that you don't really erase anything ever. Whenever you modify a value somewhere, what you actually do is add a new version, right? So in that H file right there that I'm looking at, I have the cell A1. So A1 was right here, right? That was maybe the value there. But you see that I have 4 versions of it. This is the latest one, version 4, right? And version 1, 2, and 3, now I don't see them anymore, right? Because these are past versions. But nevertheless, they are here, right? And maybe some people are interested into going back in time and seeing further versions, right? So the key is the row ID and the column name and some version number, right, in this order. So this is why you have multiple versions of the same cells. And the versions are linear, right? You have version 1, version 2, version 3, version 4, and every time you just create new versions whenever you update or create a new cell, all right? Now I put a little thing right there. What do I mean with that? I put basically a row here with a little lock. That means that for the purpose of creating these versions, whenever somebody in the company that owns the HBase cluster, so when an employee modifies a table, it locks the entire row that they are modifying. It means that while the update occurs, nobody else can touch that row. You basically have full control over the row, and that prevents spaghetti, right? Because then you cannot have Alice and Bob modifying the same row at the same time, right? So you basically take a lock, that's what it's called in computer science. You take a lock on the row, then you modify it, you create the new versions for the cells, and then you remove the lock, and then somebody else can modify that row. This is how you get these linear versions, right? Version 1, version 2, version 3, maybe it was Alice, then maybe it was Bob, and so on and so on. All right, so per row. But of course, you might have Alice modifying the row right here and Bob modifying the row right there at the same time. This is no problem, right? As long as they are not touching the same row at the same time.
So we have a question. Why don't we just lock one cell, but an entire row?
That's a design decision. It's a totally legitimate question. You could even lock the entire table if you want, right? So it can be the table, it can be the row, and it can be the cell. In fact, all of these answers are correct. You could absolutely design another technology where the level is the cell and another technology where the level is the table. It's really a design decision. We'll see that it has to do with the way that it is stored, that the rows, when you look at the H file, since the row is the first part of the key, they tend to be together in this H file, right? So it's more efficient if you modify together what is together right there. Right?
Another question is that, is lock only in writing, not in reading?
Thank you very much for this precision. Indeed, maybe that wasn't clear. Indeed, when I say the lock right there, it's only for modifying, for writing, but anybody else can still read. That's absolutely fine. So thank you very much for this precision. It's absolutely true. The lock is only for modifications.
Okay. Another question, it's this direct message to me. Is it possible to have a versioning for the entire table so that we can restore to previous version of the whole table, not row by row?
I think if you want something like that, you would have to design it yourself, in the sense that HBase doesn't support it natively. But the idea here is that, in essence, having a granularity, it's called the granularity of the versioning, basically, cell or row or table. If you have a granularity of the versioning at the cell level and looking at the row level, it's actually even better than the versioning of the entire table. Why? Because you could consider that every time you modify the table and add a new version to a row, you are in fact creating a new version of the table. Why? Maybe I can add a precision here and it will become very clear. Here, I set version 1, version 2, version 3, version 4 to simplify for pedagogical reason. What the version is actually a timestamp. It basically says, for example, March 29th, 10:30, right? It's version March 29th, 2022 at 10:30 a.m. GMT +2, right? And when you realize that, then you see that it doesn't matter if we do it for the entire table of the entire row, because whatever point in time you give me, for example, if you tell me, okay, January 2nd, 2000, or maybe I'm going to say 1955 for those who are science fiction fans, 1955, and then I can just find exactly this snapshot for every single cell in the table, right? Do you agree with that? That what we are doing here is even better, and you get what you ask for, the versioning of the table, for free, actually. Does it make sense?
Yes.
Yeah, all right, perfect. Okay, so let me continue. Okay.
We have another question. Isn't the lock logic the same as in HDFS, which means one is writing, many can read?
Yeah, that's pretty much it. That's pretty much it. I'm not entering the details of that because this is something that we teach to computer scientists, right? The details of the lock, mutual exclusion, mutex, and so on and so on. It's very complex to actually implement. But on the high level, for the purpose of this lecture, yes, it is the same thing. You just lock for writing and anybody can still continue reading. And you can consider that it is the same thing in HDFS and in HBase. All right? Okay, for HDFS, it's a file level. And for HBase, it's a row level. All right, so we have these versions. All right, so now this is the display of the key values nicely arranged as a table with two columns, the key and the value. In practice, it's a file on disk, right? So the file is just made of the key values one after the other, right? Just top down here, I go left to right here. So it's just a concatenation of all the key values. This here is what is stored in HDFS. Now, if I zoom in, what is there in a key value? Well, there is all of that. There is obviously the key and the value, right? But there is also something more. You also store the length of the key and the length of the value, because this tells you when you stop here. Otherwise, because this can be stretched, right? You don't know the size here. So you store here on 32 bits the length of the key, on 32 bits the length of the value, and then you know exactly how much to read, you know exactly how much to read, and then you're done, and that's the next key value, all right? Let's zoom in even more. Let's zoom in even more on the key right there. So what there is in a key will not surprise you, because I already told you there is the row ID, there is the column, but the column is the column family plus the column name, right? So this identifies the column. The timestamp is for the versioning, I told you. And we have an additional marker that is for deletion, because when you delete, you don't actually delete, you just mark as deleted, right? So then you have this little, it's a little Boolean that you set to either not deleted, deleted, and that tells you whether that has been deleted or not, all right? Okay. This is a very important point in big data. This notion of when you delete, you don't actually delete, but you mark for deletion. This is a very common thing to do. Of course, when you have to implement, for example, the European Union directives on data protection and so on, you are actually forced to actually delete, right? But this you can do later. You can do a whole scan of your entire database and recreate everything by dropping all the data that you need to delete, right? But we'll look into a bit more into this. All right, and now we also have the row length and the column family length, because we need to know how long that is. That can vary, right? And the column family. We don't need the length of the column qualifier just because it's a subtraction. We already know the length of the key from here, the key length. So we know the length of the key. This is fixed. This is fixed. We know the length here. It's always 32 bits, always 32 bits. We know the length here. We know the length here. So if we subtract all of this, minus this, minus this, minus this, minus this, minus this, minus this, then we know the length of the column qualifier. So this is why I don't have a length right there. Any question?
Yes. Are the H files very large since we increased block sizes in HDFS to support larger size files?
I'm coming to it. You will see that they actually grow in size as you use the database. They double regularly. But I'll come to that. I'll explain exactly the detail of how the H file is actually the life cycle of an H file, right? I'm just postponing, but you will see. Okay, and yes, they can be very large. They can become very large. Okay, so now let's look into an H file again. It turns out that when I read the key values in an H file, we again have blocks, but it's not the HDFS blocks that I'm talking to here. It's not the 128 megabytes blocks. These are smaller blocks, and these are not blocks of bits. These are blocks of key values, right? So the green block, the yellow block, the red block, they always stop exactly at the end of the key value. And the default is that they are roughly 64 kilobytes, but unlike HDFS blocks, they can be bigger because if there is a larger value in there, then the block will be a bit larger, right? And then you stop the block. So this is an approximate size of the block. And that allows us to store the key values in zones like this, right? I call them Hblocks just to distinguish them from the HDFS blocks, right? So right here, I'm really talking about the blocks in an H file, the blocks of key values. So what I have with the blocks is that I can arrange some index structure. So this is the actual H file with the sorted key values. And here I have an index that tells me, okay, key 1 is the first key in the green block. Then I have key 5 that is the first key in the yellow block. Key 11 is the first key in the orange block, and key 17 is the first key in the gray block, right? This is the index. This index that also is stored with the H file is something I can load into memory when I read the H file, right? So I can load just that part in memory, and this I leave on the disk. I load that part, and if I want to look up key 14, for example, in memory, I can figure out that key 14 is between 11 and 17, right? So in memory, I immediately know that this is in the orange block, and then I only need to fetch the orange block from the disk, right? So this is just this block that I will need to read, and then I will find key 14 right there in the block. All right, so this is how it works, and this is why we have these Hblocks inside the H file. All right. Now, I will start introducing to you the mechanism of the way we store and create the H files with these key values. Let me first zoom out, a big zoom out, take some distance and summarize the levels of physical storage. So the highest possible level is an entire table, right? So a table in HBase. Inside the table, we have regions, right? A region is just an horizontal slice of the cake, right? So we have a region, it's a collection of rows. Inside the region, we have a store. This is when I also slice on the column family, right? What do I have inside the store? I have an H file because I told you a store can be stored as multiple H files, right? So I have an H file. What is an H file made of? It's made of H blocks. And what is there in an H blocks? There are, anybody? Just checking you're following. What do I have inside an H block?
Key values.
Absolutely, the key values, absolutely. You see? So keep that in mind. This is the entire hierarchy, right? A table is made of several regions, is made of several stores, is made of several H files, is made of several H blocks, is made of several key values. That's a hierarchy, right? Okay. Now, here's the problem. People are going to keep modifying my table, right? Alice is going to add a tuple here, and Bob is going to modify a value there, and so on, right? But they are modifying at random. The problem that I have is that when they modify something at random, we need to modify a sorted collection of key values because this is all sorted here. So whenever somebody modifies something, I have the problem that I have to push down everything else here. And that looks like an impossible problem. How can you even modify an entire sorted list, right? It's like you go in a shop and you're trying to insert yourself into a queue that forces everybody else to step back, right? So it just doesn't work, and we have a mystery here. How can we even do something like that, right? The only way that we can write an H file to HDFS is in a single time, right? We just write down an H file and that's it. Yes, we have a question.
We have a comment. Can we store it as a tree?
Almost, yes. That's the log structured merge tree. So there is a tree that is going to come, but you will see very soon. It's the mystery that I will solve. Yeah. In fact, this is kind of a two-level tree, right? Where you have the first level that is the index and the second level that is in there. But we'll see that it actually goes deeper than that. Okay. But what I want to make sure here is that you understand the mystery. How can it be that I can efficiently handle it when Alice or Bob modifies a value somewhere, and it looks like I have to rewrite the entire sorted list of key values? That sounds like just amazingly slow, right, to do something like that. So how can we insert new values in an efficient way? Well, I will give you the answer now. So on disk, we have tables that have region, that have store, that have files, that have HBlocks, that have key values. What actually happens is that the H values, they are all on HDFS in these H files, but these are only the older ones that got written to HDFS. What happens when Alice inserts a new tuple, it's not going to immediately write it to HDFS. No. Instead, it's just going to put it in the memory of the region server, right? So whichever region server is responsible for the region to which Alice is writing, the new key values are just going to be in the memory of the region server, right? Not on HDFS. And here you know that this is efficient, right? You know that in the memory of your computer, you can just store whatever you want. It's random access, right? So you can just access anything anywhere and it's fast. So we put all the new fresh key values in the memory right there. This is called the mem store, right? And mem store. Okay. Now, if Alice and Bob start writing to HDFS, create new cells, create new versions when they modify something, even deleting a cell is actually creating a new key value with a marker for deletion, right? So what's going to happen is that the memory is just filling itself with the new incoming key values arriving from Alice and Bob. So it's filling, and this is all added in memory. And at some point, the memory is going to be full, right? Because they will have created so many key values that we just cannot add anything anymore. So what's happening when the memory is full? That's something you can guess.
Save it to the disk.
Yeah, exactly. We save it to the disk. How do we save it? In what format? As an H file. Exactly. So this is what we do. We just write it to the disk as a new H file. And that, of course, implies that we sort the key values. Actually, we keep them sorted in memory. And that way, we just need to write them down in the order. And here we create the HBlock, the index, and so on. And we create a new H file. The name of that is called flushing. We basically flush the memory. We flush all the key values to one H file on HDFS. And you see that now there is no problem at all because I just write it just once, the H file. And I write it directly in the sorted order of the key values that I had in memory, right? So that's wonderful, right? This is how the problem is solved. I just flush. There is an extra precaution that I take though, because what happens if I have an electricity, a power outage before I had a chance to flush, then I might lose data, right? And I don't want to lose any data. So what's gonna happen is that before I add the key values to the mem store, I always log them into an HLog structure. It's very similar to what we saw in HDFS in the name node with the snapshot and the journal that keeps track of the new updates. But the order in which the key values appear here is the order in which Alice and Bob created them. It's not the order of the key. So this here is very easy to do. It's just append. I just write a journal with a list of all my changes. And then I add it to the mem store. And this is stored in HDFS, right? The HLog right there, I can put it in HDFS. This is called the write-ahead log. Why write-ahead log? Because I write ahead of when I put it in the mem store. And now I'm fine if there's an electricity outage. Yes?
So we have a question, but it's not sorted. Key 17, for example, will be in two places.
Yep, absolutely. But I don't care. Why don't I care, it's because this is only a backup plan. This here is only for the case that I have a power outage. If I don't have a power outage, and most of the time there will not be power outage, then I will not even need to use it. The real place that I'm actually looking is here, and here it's sorted, right? So this here is only a precaution just in case. And of course, if there is actually a power outage, then maybe it's going to take a while, like half an hour in order to restore my data, but this is fine because these things are exceptional, right?
Okay. Another question is that isn't the write speed to HLog way slower than to memory, even if we consider sorting?
Here, let me put it, I will explain to you with the MapReduce and also with the HBase that when you actually create a new block in HDFS, a new file in HDFS, there is something called short circuiting. Because I told you that the region server that is responsible for doing all of that is also a data node. As a data node, it also has a local copy because I told you now I'm putting the pieces of the puzzle together. In the HDFS lecture, I explained to you that the place where you put the first block of a new file is on the same machine as the client. Now, who's the client? It's the region server doing that. And that client will put the first block of every, when it happens to the HLog locally on the machine. So I'm just writing on the local disk. I'm not going through the network or anything when I do that. This is the reason why it's actually reasonably fast, right?
Yes, another question is that, so the mem store also get back the previous cells?
The mem store also, no, it's only the fresh cells. So the previous cells, they are still here. They are not in the mem store, they are only here. And these are only the new cells. So this is why I have multiple H files now. I have this with the older cells and this with the newer cells. There is no replicate here, it's distinct. Did I answer your question?
Maybe I can do it with the audio.
Yeah.
So if on the H file on the left, I have key 12, 13, 14, 15, 16, and then I change only, say, 12 and 16.
Yep.
Should we copy 11, 12, 13, 14? Because then it's not ordered, like we have some that are on the left and some that are on another file, and it's not sorted anymore.
Yep. Well, it's sorted within here and it's sorted within there, but you need to look at both places if you want to query. I'll come back to that. And this is exactly, you're putting your finger exactly on the challenge, because there is the challenge that first it takes time to write an H file. So we solve it by only flushing when the memory is full. And then we have the challenge that we need to read from multiple H files. So we don't want too many H files, because if we end up with 1,000 H files, we have a problem, right? So you're absolutely correct that this can be a problem, that we have to look at multiple H files. And I will give you the solutions in just a few minutes.
Okay, thanks.
Okay, thank you. Any other question?
No, there's a comment, but it's related to the previous.
I think it's addressed, yeah.
Yes.
Yeah. So I think, okay. All right, so the write-ahead log, okay, and now it's in the mem store, okay. And so what happens is that I flush whenever the memory is full, so I reach the max mem store size in a store, or maybe when over the entire cluster, I have too many new key values, and maybe I start feeling nervous that there is now a lot of pending changes. So I can also trigger a flush when on the cluster I have too much. And also when the write-ahead log grows too big, meaning that after a power outage, it's going to take too much time to restore, then I can also trigger a flush, right? So you see there are several ways that a flush can be triggered. And whenever you trigger a flush, you just write one H file out of the memory. So now coming back to the question that you asked earlier, and now I'm starting to touch all of these points. If you want to read from a store because somebody has a get query or a scan query, where do you need to look from? Where do you need to look in order to get the key values? Well, the answer is everywhere. You might have very old key values in there that are from an older H file. you might have more recent key values that were flushed more recently in the H file, plus you might have fresh ones that were just added a few minutes ago and that haven't been flushed yet. So you need to look everywhere at the same time because it could be anywhere. And then you assemble all the key values you want. Then you eliminate the older versions. So if you see several versions of the same cell, you just take the latest. And that's it. So this is how you read from a store. And indeed, the challenge is we need to look from all these places right there in order to reconstruct the actual table. So as a consequence, and this is why you had the next question, we do not want to have too many H files, because if we have too many H files, then it just becomes a nightmare to read from so many places. So what do? There is something else to the flush called the compaction. When I have too many H files, like here I have 3 of them, what can I do? I can merge them into a single big sorted H file. This is called compaction. So I had 3 separate H files. Now I have one single bigger merged H files. What's really, really nice is that computer scientists know how to do that very efficiently. Because if you want to merge several sorted lists, you can actually do it in linear time, which is extraordinarily efficient. It's like when you play poker and you have 2 piles of cards and you just put them like this, right? So you just concurrently go through the list and write as you go to the output, right? So the one thing you need to remember, if a computer scientist is given several sorted lists of key value pairs, they can very efficiently merge them into a bigger single sorted list. That's the one thing to remember. And this is called compaction, right? So now we know when to flush. We know that we can compact, but we still have to decide of a strategy. When do I compact, right? Do I need to compact every single time I create a new H file, or do I need to compact maybe every once a week? Maybe I don't want to do it too often because all of that takes time, right? And we have also a solution for that. This is actually the great news, and I think the people who designed this are really geniuses. This is with the log structured merge trees, LSM trees. B+ trees are for indexing in relational database systems. I'll come back to them in the MongoDB lecture in a few weeks on document stores. We'll look again at indices. If you've been in information systems for engineers, you also saw these indices. These are called B+ trees. With B+ trees, the issue is the latency, is that you need to access some parts of it, but every time you need to wait until the head of the hard drive is at the right place. But in big data, the problem is completely different. We want to have a system that is massively, moving data around. It means we want to be transfer time bound. You want the energy of the cluster to go into writing in batch processing many key values at the same time. And this is what LSM trees are designed for. The idea is that you asked earlier for the size. What is the size of an H file? Well, the answer is any size, because what's happening is that we have multiple levels of H files. We have the small H files that are the more recent ones. And when we compact them, we get bigger H files. And when we compact them, we get even bigger H files. And actually, we'll see that it doubled in size, right? So maybe the smaller H files, I don't know, I'm just doing that at random, but maybe it's, let's say, 100 megabytes. And then these are 200 megabytes, and then 400 megabytes, and then 800 megabytes. So I basically have them in all t-shirt sizes, the H files. And the longer you use your system, the longer you keep modifying your H-based data, the more you will flush, the more you will compact, the more you will get heavier and heavier and heavier H files as you go. And of course, we need to do it in a very smart way because we don't want to compact too often. One strategy could be every time you flush, you compact everything again so that you only ever have one H file at the same time. This is highly inefficient because you're going to spend your whole time compacting every time. So the solution is do it like this. Do we have a question? I heard some noise.
No.
No? All right. So here's comes the animation, right? So fasten your seatbelt. Now comes the animation of the log structured merge tree. So Alice and Bob start using the database. They haven't stored anything so far. It's completely new. They've created a new table in HBase, and they started adding a few key values. So they accumulate in the memory store and there is nothing yet in H files. At some point, the memory becomes full. So what do we do when the memory is full? What is it called? It starts with an F.
Flush.
Exactly, we flush. So we flush the memory to an H file. So here it disappears and now it's in an H file, a small one, right? Because this is just the start and this is roughly the size of the memory, if you want. Okay. Now Alice and Bob continue to write to HBase and create new fresh key values in there, right? What's happening when the memory is full is we flush again. So now we have two H files, all right? And here comes the trick. In a log structured merge trees, whenever you have two H files of the same size, what is the verb? Merge. There is another verb for merge. What do we call that?
Compact.
Compact, exactly. You compact them. And then you get one double as big, twice as big H file. Okay. And now Alice and Bob keep using the system. We flush. So now we have one double size H file. It's like the double cheeseburger and the cheeseburger, right? So we have the twice as big and the single size. And I flush. Then I flush again. Now I have two. So what do? I compact them. Now I have two H files of that bigger size. And I said that whenever we have two of the same size, we compact. So now I have an even bigger one. This is the size 4 cheeseburger, right? So now I have an H file there. Then they continue to use the system. I flush, continue, I flush, two of the same size, I compact them. Now I have two H files. They continue to use it, flush, continue to use it, flush. And now you see how it works, right? I just keep flushing and flushing and flushing and flushing, and I keep pushing to the right and compacting to bigger and bigger sizes. This here is the solution to the mystery of how we can efficiently keep creating data on HDFS in a way that is scalable.
Yeah,
do we have questions?
Comments in the chat. It's like the game 2048, which merges the numbers.
Yes, I actually was trying to because it rang a bell also in my mind. And yes, this is exactly that game. It is exactly the 2048 game. So look it up if you don't know that game and play it. This here is a 2048 game with your data. I love that. Thank you so much. This is a comparison that I will continue to use in the future because this is exactly what it is. Right. So this is the 1, this is the 2, and this is the 4. And whenever two of the same time touch, then they double. All right. Any other question?
Is there an upper limit to the size of file? Is it ever efficient to split it back in sorted subfiles?
Absolutely, there is a limit because that's what I explained last week, that when a region grows too big, you can split the region into two regions. And that, of course, will mean that if you have two big H files, you can rewrite these H files, you can sort them again and write the first half in an H file, the second half in an H file, but then you make it different regions. You say, okay, they live their own life. Okay, this is done at the region level. Okay, there's one more improvement that we do is that the HBlocks there that we access frequently, we do keep a copy in memory, but it's not the name store. These are the fresh ones. Here is just a copy in memory of the most used key values in there. And that way we can also sometimes very efficiently without disk access, look at the data. All right. So it turns out that there is a special table in HBase that's called the meta table that stores the locations of the tables, right? And that way, when you want to create or delete or update a table, you go to the HMaster, but you don't know where to look, right? So you need to fetch the meta table, which is somewhere. So you basically know where it is. I'm not going into the details of that. It's with the technology called Zookeeper. I love that name. But basically, you have one of the region servers that hosts the meta table that knows where all the regions are located in there and where the data is. And then we can tell the client where the region server locations are, and then you go get them. So it's a bit similar to HDFS, the idea that you ask for the block IDs and then get the blocks, except that unlike HDFS, that data is stored on one of the region servers and not in the HMaster. That's the difference. Okay. Okay. So in HBase, you have REST, you have Java, so you have many ways to access it. Oh, we have the bell. Okay, let me give you a break. I'm actually almost done on HDFS. So I'll continue right after the break for the very few slides that I have left, and then we'll start with some data modeling. So I'll see you in 10 minutes at 10 past 11. Thank you.